Good morning, everyone, and thank you for joining this session. So today I will speak about the new insights into the dynamics of explosive lunar volcanisms through the textual analysis of the 74001 by 2 glass beads. So a brief background of the sample that I am studying. So this sample was collected during the last Apollo mission, which was the Apollo 17, which is marked by a star, and it was collected from the Taurus Littrow Valley from the rim of the Soti crater, which is you can see on the right side of the image, marked in the orange patchy area. This drill core is approximately 70 centimeter in length and is divided into two halves. The bottom half is known as the 74001 and the top half is known as the 74002. So what are my motivations of studying this drill core and what are my research objectives? So we know on Earth, research has shown that in the pyroclastic deposits from volcano, vesicle studies has shown that it controls the dynamics of the eruption that takes place on the Earth. Previous studies on this drill core has suggested that there are vesicles present in these samples, but none have been quantified. So with that thought, I am studying like why we can't use these vesicle textures present in this drill core and try to say something about the volcanism that took place around 3.7 billion years ago. So my first step is, are they volcanic in nature? Second is analyzing the texture present across this drill core. And finally, understanding the dynamics of the eruption from the vesicle texture. So the first step is we did some physiochemical studies, and under the microscope, we found no shock texture or presence of any exotic materials. And when we did major oxide analysis using EPMA, we saw that there is clustering of the major oxides when plotted against magnesium oxides. So this show that there is intra and inter sample homogeneity. So I have data from 6 different depths across this drill core, and we can see in the plot that they are falling in a very small zone. And they also have a high magnesium to aluminum ratio of more than 1.6 and a calcium to aluminum oxide ratio more than 0.75. So based on all these criteria, we can say these are pristine volcanic glasses and not impact origin. So now let us look at this drill core. So here it is a schematic representation of the sample depths from where I am analyzing. And this drill core is mainly composed of orange and black glass beads. The difference between orange and black beads are they are chemically same. The main difference is orange is completely hollow hyaline glass, while the black is crystalline in nature. And orange is much more common at the top of the drill core. And as we go to the bottom of the drill core, black glass becomes more dominant. And I'm thankful to the Material Allocation Review Board for providing us samples from equal regular interval across this drill core. When a volcano erupts and a magma rises through a volcanic conduit, we know due to decompression, gases exhaust and they form bubbles. Now, these bubbles are often preserved as vesicles in the pyroclastic deposits. And in my samples, I have seen different types of vesicles present. So here are 4 examples of vesicles, and remember them, like I will discuss them more thoroughly in my upcoming slides. So over here, we can see a single vesicle present at the center of the grain bead. We are seeing 2 vesicles on the top right corner. In the bottom right, in the bottom row, we can see that there are 2 vesicles which are merged. And finally, we can see a vesicle which was on the rim around the rim of the glass bead which has escaped. So let us see how these vesicles vary across this drill core. So over here, I have beads that range from 20 micron to 1000 micron. And surprisingly, no vesicles were found in beads that has a diameter more than 500 micron. So I'm on the first diagram on the left, I am plotting that vesicle radiance against the bead diameter. And we can see with an increase in bead diameter, there is an increase in vesicle radius, which is fairly expected. But when the vesicle volume was plotted against bead diameter, it can be seen that vesicles in the less size of bead, they are occupying a larger volume compared to the vesicles which are present in the greater bead size. And the color over here is the lightest shade represents shallow depth and the darker shade represents deeper depth within this drill core. Now I said that there are orange and black glass beads within this drill core. Now let us see how these vesicles vary within these individual black and orange beads. So over here again on the left, I am plotting vesicle radius against bead diameter, and same the color scheme is same again. Shallow color, lighter shade represents shallow depth, and darker shade represents greater depth. We can see that the smallest and the largest vesicles are mainly found within the black glass beads, and similarly, like vesicle volume is much more, slightly more in the smaller sizes, and we can see like irrespective of the glass color or the bead color, we can see the vesicle volume is fairly low when compared to terrestrial samples, and this might indicate a fine fragmentation process and loss of volatiles. So while studying the different vesicles across this drill core, I came across some unique vesicle texture which is known as the vesicle coalescence. And over here, the physical properties of this bead, vesicle radius, and throat length or IBMF are listed here. Now, to bring us everybody on the same page, I will briefly explain what is vesicle coalescence mechanism. So let us imagine in a pocket of melt, there are two vesicles which was initially separated by some distance at delta zero. With progress in time, the melt between these two vesicles might drain away and these vesicles come closer. With further progress in time, these vesicles might merge and a hole will be formed between these two vesicles. Now this completes the coalescence process, and all this is happening while the melt is cooling down, because these are found between the pyroclastic beads, where these beads are cooling down from the liquidus temperature to the glass transient temperature. And if given enough time, this hole might grow and it might relax its film, and this is known as the hole growth process or the film relaxation process. Now over here we can see that there are three different time scale. One is the coalescence time scale where two vesicles are merging. Secondly, there is the film relaxation time scale, and finally there is a cooling time scale where the pocket of melt is cooling down. And from this we have a fairly easy hypothesis. If the time taken by coalescence and relaxation is much more than the cooling time scale, we will have incomplete bubble relaxation shape. Whereas if the coalescence and the relaxation time scale is lesser than the cooling time scale, we will see vesicles will relax its throat completely and might form complete spherical shape. Based on this formulation, I plotted and we tried to understand that at what point of cooling time scale or cooling history the coalescence might initiate or should initiate to protect or like preserve the shape that we are observing under the microscope.
2 minutes.
Thank you. So we plotted on various parameters, and we can see like if the coalescence starts right at the vent exit, it takes place, the coalescence is completed under 2/10 of a second, and from the point of coalescence, this vesicle starts to relax, and when the it takes like less than 3/10 of a second to relax its film and reach the observed throat length. Over here in the table in the bottom two row, we can see that total time for coalescence and relaxation is almost same with the cooling time scale, and that's why we are seeing that incomplete vesicle relaxation shape. So our results suggest that despite of like various kinds of heating or cooling parameters or like throat length, we say that coalescence has to initiate right at the vent exit. And if the ambient surface temperature is too low, and if there is a presence of hot plume or any transient atmosphere, there can be hindrance of coalescence because the cooling time scale becomes too low. So the conclusion in the future works are like the pristine glass beads, which are like more orange at the top of the drill core and black at the bottom of the drill core, are like volcanic in origin. They cool down pretty fast, and like the cooling time scale depends on the size of the glass beads. And in the future, I want to investigate like what are the fragmentation processes that took place during their deposit that gave us a like bead size ranging from 20 to 1000 microns. And finally, I want to investigate the relationship between like any presence of any transient plume, the bead size, or the ambient surface temperature to further constrain where coalescence and relaxation should start or stop to preserve the texture and finally constrain the existing cooling rates of these orange glass beads. Thank you.